floods and tsunamis were restored to GR structures. The total wall length of these GR structures is now about 200 kilometers. Any problem during and after construction has not been reported, while very high cost effectiveness has been validated. The first topic is the recent typical GR structures for railways in Japan. This is showing a network of high-speed railway in Japan, Shinkansen. So first one is 1964, and the red part is under construction. So I'll show you the typical site for this Shinkansen. At this site, here R means GR's retaining wall, here, and A means GR's bridge abutment. You see here the bridge abutment. In total, 33 were constructed for this line. GR's integral bridge, I'll explain this later. And B is GR's box culvert. And T here is GR's tunnel entrance exit protection. This is a cross view of the site. This is a box culvert, GR's box culvert. This GR's retain walls. And this is GR's tunnel entrance exit protection. This is showing GR's bridge abutment under construction. So first, the shallow ground improvement is made where necessary. Then the this reinforced backfill is constructed. Then floor height rigid facing is constructed. Then bearings, and finally girders. And this is a complete one. For this place, this line will be opened this September. At this place, number of GR structures constructed. For example, GR bridge abutment 78. This is 89% of total bridge abutments. This is a GR retaining wall surrounding the depot of this site. The highest wall height is 12.4 meters. And this is showing how GR's bridge abutment was constructed. First is the bench cutting of the natural slope. Second is the construction of approach field. This is the grit reinforced, well-compacted, lightly cement mixed gravel soil. Third is the compaction of the backfill, at least 95% of the max at obtained water content by modified proctor. And this is showing the arrangement of the grid layer, and this is completed approach field. 6 is the completed GR's bridge abutment after the construction of floor height rigid facing. So, and this is a GR tunnel entrance exit protection. So this tunnel entrance exit protection is constructed in this way, backfill, and so on, so on. The point is that this floor height facing is not structurally floor height rigid facing is structurally separated from RC turning lining to avoid the stress concentration. This is showing how the GR's internal bridge was constructed. First is excavation of subsoil. Second is the construction of approach field. Here's a zero grit reinforced backfill, and this is a left backfill. Then the construction of floor height rigid facing after the deformation of the backfill and subsoil has taken place sufficiently. Then the PC girder is located here. This is a cross-section of PC girder. Then finally, the structural integration of both ends of girder to the floor height rigid facing. Then construction of other structures. So this is completed DR pressure abutment. So this is showing the length of DR structure constructed every year. And starting from 1989, today it reached 200 kilometers. So this year, the construction of high-speed railway was restarted. Then we had a number of earthquakes like this. So we have many stories by these earthquakes, which I will explain later. And this is showing the location of DR structures constructed in Japan, and several places are in Indonesia and Philippines now. And I like to emphasize that there is no problematic case during and after construction in all these projects. So no problem, zero problem so far. This is the DR's retaining wall at the port for the mass rapid transit in Jakarta. And this is mass transit. And here the depot. The port is surrounded by retaining walls. And this part is DR's retaining wall. This is DR's retaining wall under construction before the construction of floor-height ridge facing. This is after the construction of floor-height ridge facing. This is the view here. So this is the crest of floor-height ridge facing, and you can see the railway track is constructed very close to the floor-height ridge facing. You can see. This is a DR structure for railway in Manila, Philippines, from here to here, and many DR structures are now under construction. For example, at this site, here is a DR retaining wall, and here is a DR internal bridge. Here is also short span, but this is DR internal bridge, and so on. This is a view of DR retaining walls for both sides under construction, like this. This is a cost estimate, cost comparison of the cost for conventional RC viaduct. When this cost is 1, the cost for DR retaining wall in this case is 0.5 when the ground improvement is not performed. When the depth of ground improvement increases, the cost for DR retaining walls increase. But even at the depth of 10 meters, this is still 85%. This is a cost comparison made for a high-speed train in India. So in this case, is a conventional cantilever RC retaining wall having a pile of 20-meter length. And this is DRS retaining wall without piles. In this case, the construction cost for DRS retaining walls is only 0.32, and the maintenance cost is 0.5, and the total cost for DRS retaining wall is only 0.33 compared to this conventional retaining wall. Even when there are no piles for conventional retaining wall, the cost is for DRS structure is still this low. The summary of the first part: DR structures with floor-height ridge facing have become the standard railway soil structures in Japan. A number of DR structures were constructed in place of conventional type embankments, retaining walls, and bridge abutments. And this is due to that, compared with the conventional type soil structures, DR structures exhibit higher performance under long-term ordinary conditions and against earthquakes, heavy prolonged rainfalls, floods, and tsunami, and lower costs for both of construction and long-term maintenance. So next, several theoretical and technical bases for this DR structure will be explained. Second topic is in extensive versus extensive reinforcement. and flexible and stiff facing. So we have two types of reinforcement in extensible and extensive. We have two types of facing, one the flexible one, not developing high aspect pressure on the facing, and the stiff one, developing high aspect pressure on the facing. So we have four different types by this combination of two factors. This A is the metallic skin facing, this one, so-called tailor-made. And this is a discrete concrete panel with metallic strips. So this is the wrapped around facing using a zero grid. This is a modular block facing using a zero grid, D, and E is a full height grid facing using a zero grid. This is what we developed, E. Previously, many considered that facing is only to prevent the splitting out of backfill and to achieve a small wall deformation and a high wall stability. It is necessary to keep low, not high, keep low the earth pressure on the facing. So flexible facing is A and C is sufficient. However, we have often observed that when using a flexible facing A and C, the earth pressure on the facing is low, but the wall deformation is generally large, indicating the paramount importance of using stiff facing. That means when the facing is flexible, we have very low earth pressure here. Very low earth pressure on the facing means low tensile forces in the reinforcement, in particular at low places. So connection force is zero. So we have a low tensile forces. Then in the active zone, the low confined pressure and therefore low strength and stiffness of the backfill. Then we have a large wall deformation and low stability of the wall. So this is a embankment which constructed in 1982. This is the clear backfill and the wall face is wrapped around, so very flexible. So we had a very large deformation of the wall. So we learned that this does not work. So on the other hand, we have consistently observed that at the stiff facing that is firmly connected to the reinforcement layer, case B, like this, and case D, and case E. In this case, large earth pressure develops, which results in a small wall deformation and high wall stability. This means that when the stiff facing is firmly connected to the reinforcement, we have a high earth pressure here. That means a high connection strength. The high earth pressure on the facing means high tensile forces in that reinforcement, even at low levels. This means in active zone, we have a high confined pressure, therefore high tensile, a high strength and stiffness of the backfill. Then we have a small wall deformation and high stability of the wall. This is the observation of such high connection force with tailor-made. This is during construction. The connection force develops during construction of the wall. Then we have high tensile forces. So you can see that this is distribution of the tensile force in reinforcement, this metal strips. So we have a high connection force. So then this results in the stable behavior of wall with small deformation. So previously, many considered that for small deformation and high wall stability, discrete panel facing or modular block or B or C is sufficient, but full height rigid facing is not necessary. However, we have often observed that the use of full height deformation will increase the wall stability. So this is a two-tested embankment we constructed 1987 to 1988. This is the sand backfill. This is the clay backfill. This is before the construction of full height rigid facing. This is a completed full height rigid facing. So we observe a long-term behavior of this model wall. So discrete panel facing shows some noticeable deformation for 2 years. But the rigid facing did not show any deformation or displacement. Same thing for other sections. So we performed a loading test to bring this wall to failure. Each section having a discrete panel facing. By loading here, the buckling of the facing here. This is a cross section of this section after excavation. Here is a discrete panel fitting. Loading is here. So failure plane like this. So by this loading, this segment H exhibited this behavior. So this is average footing pressure plotted against the lateral displacement at the top of the facing. So facing segment F, this is the rigid facing, but length is reinforcement only 1.5 meter compared to the wall height of 5 meters, very short. Yet this shows a better performance. And the segment D, more stable because the length is 2 meter. Yet C, D, and H having flat rigid facing, the stability of the segment F and D was controlled by the yielding of construction joints here, because this facing is concrete facing without any steel reinforcement. So full height rigid facing for all the prototype DR retaining walls constructed subsequently are all largely steel reinforcement. So some issue about the inextensible metallic strip. Previously, many considered that for small wall deformation and high wall stability, that it is necessary to use inextensible reinforcement, such as metallic strips. This is the must. Many people consider in that way. Although metallic strips are extensible, they have the following two major potential problems. One is erosion, corrosion. The second is low pull-out strength. So this I'll discuss the second point. This is a failure of telemere wall. Relatively short metallic strips was used to reduce the amount of the excavation. This resulting in a pull-out at low levels and pushing out of the several discrete panels, finally a collapse of the whole wall. To avoid this type of failure, we use relatively long metallic strips. This can prevent the pull-out failure, but it increases the amount of the excavation while requiring the use of the anchored seat piles like this. So this increases the construction cost and construction period. So we are using a GR retaining wall with flat facing, but basic reinforcement very short. We can use this short basic reinforcement without losing wall stability due to high pull-out strength of the planar geotextile, and by using the several long geogrid layers and the use of flat rigid facing. These arrangements decreases the amount of excavation here, while not requiring the use of anchored seat pile. So, summary of this discussion of this chapter. Full height rigid facing firmly connected to the reinforcement layers can ensure small deformation and high stability of the wall even when using a relatively short so-called extensive reinforcement. That is, for example, the grid. And full height rigid facing is also a good solution for good durability and aesthetics. One remark is that at the same time, good compaction and good drainage of the backfill are imperative for a good wall performance. So next is the insight into the function of full height rigid facing. So first of all, I like to say conventional retaining wall is a cantilever wall. Yeah. So then we have a large forces in the facing, and then we have a large overturning moment and large lateral load at facing base. So we have a large stress concentration here. So, and unstable behavior, particularly against such loads. So we need a massive, strong earth facing structure supported by a pile foundation. This is the collapse of gravity type wall during 1995 Kobe earthquake. This is a kind of cantilever wall. You can see overturning failure. This is me. So this was designed using a seismic coefficient 0.2 with a safety factor equals 1.5. Yet, seismic load is so strong, we have this kind of failure. On the other hand, GR's retaining wall is not cantilever structures. So with respect to force equilibrium A along a potential active failure plane, at each level, active earth pressure is resisted by the tensile reinforcement layer, unlike cantilever structures. With respect to the equilibrium B along the back facing, again, at each level, the earth pressure on the back face of facing is resisted by the tensile force at connection between the reinforcement and facing. So this is showing a paramount importance of the sufficient connection strength. So continuous full height rigid facing is a continuous beam supported by many reinforcement layers at a small span, actually 30 centimeters. As a result, we have very small forces in the facing, so a simple function structure is sufficient. And also, we have a small overturning moment and small lateral load at the facing base. So we don't need a pile foundation, and the wall can be stable even against such loads. Or no. This is showing a GR's retaining wall before it's 1992, immediately after completion. This is the same wall a week after the 1995 Kobe earthquake. We observe a very high performance during this very severe earthquake. Yet, however, a limited amount but a noticeable shear deformation is about 26 meter by 6 meter equal to 4.043 was observed at the highest section. This shear deformation is due likely to use of a short zero grid, only a 2 meter long. So this is only 40% wall height for 5 meter. So then, what is the necessary and sufficient length for wall stability? We perform the shaking table test, so simulating a gravity type retaining wall, and also simulating this GR's retaining wall having a short textile. This was designed by the old code, so in this particular site, all the textile layers are very short due to specific space restriction. So yet this wall survived. This is showing a result of the shaking table test. This is a displacement at the top against a seismic coefficient applied. So gravity types show this large displacement, and this DRS retaining wall shows the better performance. Yet we have a noticeable shear deformation. So other conventional type, cantilever, linear type, show the similar behavior, and the zero textile wall, R1, R2, R3 are better performance. R3 have a long zero textile reinforcement, and R2 is here you can see only 2 layers are long. So higher stability R3, R2 than R1. R2, this is more stable than R1, while similar behavior as R3. And this means more cost-effective than R3 because of a less amount of zero textile and less amount of excavation here when constructed on the existing slope. So R2 is recommended and specified as a standard type in the current design code. So this is when we make a wall on the slope. This is the conventional method. This is a GRC wall, but modular block is used here. In this case, we need a long reinforcement. So in both cases, the two methods require large slope excavation and the use of temporary anchored seat piles, which largely increase the construction cost and period. Why we need a long zero textile when modular block facing is used? This is because when facing zero textile short and a failure plane become very shallow, then we have then the resistance against the lateral sliding and overturning becomes low. And modular block is not rigid enough to prevent such a local failure like this. So we use a long reinforcement to make the failure plane deep like C. Usually the minimum length is the minimum ratio L by H is 0.7. So then we have sufficient stability against lateral sliding and overturning. But we need a large excavation here. In this case, on the other hand, reduction of wall stability by the use of a short basic reinforcement layer is here in this case. This is covered by use of several long reinforcement layers and the use of flat ridge facing. This arrangement 1 or 2 facilitate integrated behavior of the enlarged reinforced zone, reducing shear deformation and increasing the wall stability against overturning and lateral sliding, particularly by such modes. And the stability against concentric load here near the wall at the crest. So by vertical load, horizontal, and we can construct bridge girder here. So this type we are now using a small amount of slope excavation and no need for use of anchored steel pile. So much more cost effective and shorter construction period than 2 methods shown here. So this is our current design. The length of the basic degree is the largest value among 35% of wall height, or 1.5 meter, or the length required for sufficient stability against overturning, lateral sliding, and shear deformation, evaluated by a Newmark method based on the 2 wedge method. So some advantage of the fluid ridge facing is a 3-dimensional effect. Each GRS wall section between two consecutive construction joints behaves monolithically, so local failure is very difficult to take place. Even if local failure takes place, the collapse of four wall hardly take place. So, and full hybrid facing can support external load here, V and H, caused by electricity supply pole or noise barrier or crash barrier and other bits like this. So then we go back to the conventional structure like this. These are costly, but there are some advantage. Limited occupied space and facing of the retaining wall can support other structures. When we use this modular block facing, the less costly, but we need a buffer zone to ensure safe operation of road and railway, so the wider occupied space. And facing cannot effectively support other structures. On the other hand, this full hybrid facing is less costly and also like conventional retaining walls and viaduct, road and railway can be arranged very close to the facing, so limited occupied space. And the facing can effectively support other structures here like this. Like this, you can this actual case. Or like this. Here you can trains running very close to the wall face and the small excavation here. This is a site in Tokyo. So summary of the function of hybrid facing. The facing is an important and essential structural component that confines the backfill, develops large tensile forces in the reinforcement and supporting other structures, so the facing should be rigid enough during service. On the other hand, facing should be deformable enough during wall construction to accommodate the deformation of backfill and supporting ground. So this is the contradiction. This contradiction can be solved by state construction. Next is the advantage to state construction of hybrid facing. This is before the start of construction, you see. Then this is a completed backfill, but before the construction of hybrid facing. And this is completed wall after construction of the hybrid facing, you can see. So this is a cross view of the wall, completed wall. So state construction is made in this way. First is the leveling part for facing. The gravel backs wrap around the textile. Next is the compaction of the first layer. Next is the compaction of the second layer. For good compaction, this vertical spacing 30 centimeter, then lift will become 15 centimeter. And there's no rigid facing existing during vertical compaction. This is the completed wall, but before the construction of rigid facing. After deformation of the backfill and subsoil has taken place, then rigid facing is constructed by casting in place fresh concrete here directly on the grid wrapped around wall face. So this is concrete form outside, and this is no concrete form inside, and fresh concrete is cast in place here. So fresh concrete enters the gravity backs through the aperture of the Z grid. Then facing connection and the Z grid reinforcement are firmly connected to each other. High connection force between the backs and facing were confirmed by field test and laboratory test. And this is a typical completed wall. So I'm talking about advantage of state construction procedure. First is completed wall exhibited very small residual deformation, the residual differential settlement between facing and backfill. And zero gravel backs protect the facing and zero grid connection. So facing zero grid connection is hardly damaged during service. And the construction of GRD wall using a compressive backfill and or on a compressive subsoil becomes possible. This is a case constructed on very soft clay deposit, 30-meter clay deposit. So, and backfill was weak soft soil, and I say very thick soft clay, and no pile foundation allowed. So these problems were overcome by safe construction. First, GRS retaining wall without full height facing, and then preloading here, and settlement about 1 meter, and removal of preload fill, the final construction of full height facing. This is during preloading fill, so 1 meter settlement. After removing preload fill, this full height facing was constructed. I took this picture 20 years after construction. So I'll skip this. Okay. Box culvert is constructed in this way, and but we have several problems by compression of settlement. So we have a bumping here and roll concentration and negative friction. So this is a really problem. With GRS box culvert is constructed in this way: shallow ground improvement and construction of the grid reinforcement embankment. We have a compression of the backfill and the settlement of the ground. Then we have construct GRS culvert. Side walls are connected to the grid layers. Then backfilling here, so no problem with bumping here. So summary, by stage construction, during wall construction, the facing is deformable enough to accommodate the deformation of the backfill and supported ground. During long-term service, the facing is stiff enough to achieve small wall deformation and high stability of the completed wall. And as a result, construction of a GRS wall using a compressive backfill and or compressive subsoil becomes possible. Next is bridge abutment and GRS integral bridge. So this is the conventional simple girder bridge. This has several serious problems. To solve these problems, first is an integral bridge. The second is a GRS bridge abutment. Third is a GRS integral bridge. With the conventional simple girder bridge, we construct first pile, as abutment, then problem starts as pressure and displacement and the settlement lateral flow. Then we construct the bearings, but this is costly for construction and long-term maintenance. We have a long-term settlement and large deformation and dislodging of simple girder during earthquake. So what is the solution? First solution is an integral bridge. This constructed in this way, piles are facing, condensed girders, and integration here, and backfill. But so a large number of integral bridges were constructed in the United Kingdom and the United States. However, there are a number of problems. First, we have this earth pressure problem, and this settlement and lateral flow problem, and the long-term settlement and sudden settlement during such load. A new problem is this. We have a seasonal thermal expansion and contraction of the girder. This develops cyclic lateral displacement. This results in a settlement here and increase in the earth pressure. This is due to a so-called dual ratcheting mechanism. When wall displaced in this way, active failure we have. When the wall is displaced in the passive direction, active failure does not move, but passive wedge is formed. The second active displacement, this active displacement is deactivated, and the second passive movement, now this active wedge does not move, but the activation of the formation of displacement of passive wedge. So active failure and passive earth pressure development take place independently. I skipped the test results. Anyway, then we go to this GS bridge abutment. First generation is this and second generation. I'll explain second generation. GRS wall is first constructed, fluid ridge facing, and girder foundation is connected to fluid facing. Then bearing is placed and simple girder placed. So this is highly cost effective and stable when compared to the conventional type bridge abutment. And this is statically determinate, so not sensitive to residual displacement of the facing that may take place during long-term service. So this is rather simple to design and construct. This is a typical case. This is a bench cut of slope and the construction of approach field. Here is a full height facing on which girder is placed. The first one was construct 203 for the high-speed train here, 203. So full-scale loading test was performed by applying a horizontal load to evaluate the stability of this DRS bridge abutment, particularly separation between facing and backfill was avoided. We observed that this is really stable and the separation strength is very high. So after this first DRS bridge abutment 203, we construct many DRS bridge abutment. After construction of the first one at Tanata, by 2022, about 139 have been constructed, including 33 for Hokkaido Shinkansen, 79 for Kyushu Shinkansen, 21 for Hokuriku Shinkansen. So that finally DRS the internal bridge. If we place a simple girder on the facing of the DRS written wall, then we have two problems. One is a high cost for construction and maintenance by bearing, and the low seismic stability of the girder at the movable bearing. So we remove these bearings. This is a DRS internal bridge. First backfill and fluid ridge facing and continuous girder. So structure integration here. So the model test we performed to confirm the stability of the wall, but this one showing a very small settlement here in the IGS, this DRS integral bridges, the textile and connection here. And shaking table tests were performed, and this is a conventional type gravity type abutment and DRS bridge abutment first generation, integral bridge, DRS integral bridge. This is lateral displacement at the top, dt. This is a basic acceleration. We have a large displacement at the top in this case, and here's also large displacement at the fixed bearing. And the integral bridge show the large displacements at the bottom. But the DRS integral bridge show nearly zero displacement at the top, and displacement takes place after connection failure between the textile and facing. And the settlement here is very small, with DRS integral bridge. But the settlement bump is very large with conventional type gravity wall and also integral bridge. So we constructed the full-scale model of DRS integral bridge, and we perform cyclic loading tests simulating seismic and thermal effects. Sorry. Then first one was constructed here. This one. This is the spine is 12 meters, very short, but this is the real first one, and for high-speed train. Then the second one was constructed here, 3 DRS integral bridges. This is after tsunami. This is a simple girder bridge. So 2 simple girder were washed away by the great tsunami from Pacific Ocean. So 3 candidates were considered to restore this one. First one is original simple girder bridge. Second one is this bridge, continuous bridge, but both ends we use a bearing. The last one is a DRS integral bridge, continuous bridge, and no bearings. This has a low cost and high seismic stability and high anti-tsunami stability. So this was adopted. So this one. This is a complete one. Total span is 40 meters. At another place, here again, this simple girder was away by tsunami. And this is the complete one. Total length is 60 meters. Central pier is only to support vertical load. And this girder is continuous. The both ends were constructed, connected to flight ridge facing. See? So DRS bridge abutment supports a simple girder at the top of the flight facing of DRS retaining wall. DRS integral bridge structurally integrate both ends of continuous girder to the flight ridge facing of a pair of DRS retaining walls. Compared with the conventional type bridge abutments, conventional bridges, these are much more cost-effective, exhibiting much higher stability against seismic loads, floods, and tsunami, and no bump right back behind the facing. They are now the standard bridge abutments for railways, including high-speed railways. The last topic is the collapse of soil structure by earthquakes, floods, and tsunami, and restoration to their structure. So this is the case here, Kobe. This is a collapse of conventional type retaining wall. This will restore to their structure. And here is another case. This collapse of the conventional type retaining wall and the failure of the slope, embankment, like this. This blue one is before the collapse, and solid one is after collapse. The red one is restored structure. This is the retaining wall. And this is during construction. And this is another side. You see the failure of the embankment on slope. This is restored retaining wall. This is retaining wall. Here's another case, is a collapse by flood. Here is a embankment between tunnels. This embankment fully washed away by overtopping flood. So this was reconstructed in this way. You can see DRS retaining wall here and DRS embankment to reduce the total amount of earthwork and increase the stability of the wall. This 1990 and this 1991, and this was 1994. And another type of collapse of conventional type cantilever wall is by scarring. Then this overturn failure then collapse or embankment. On the other hand, we can expect much better performance of GR wall with full height ridge facing. The overturning failure of right ridge facing does not take place. So backfill can survive keeping embankment service, emergent service of the road or railway. This is the collapse of the seawall by the erosion or by storm, by storm. So this was fully collapsed. And this was restored to GR wall like this. This is a picture taken during reconstruction. This is before construction of rigid facing. This is during construction of rigid facing, and this is complete one. This is a small scale failure, but a typical one, scarring and erosion of the backfill. This was also reconstructed by the technology of GRS bridge abutment like this. And here's a larger scale failure of railway embankment by scarring here. This is the complete one. The river is attacking the wall and embankment. This is before the construction of the flat ridge facing. This is a complete one. Flat ridge facing is very effective to prevent the failure of the wall by scarring here. Here is damage to many railway structures by tsunami 2001. Here the before the earthquake, a tsunami. Here the viaduct, you can see. This was totally collapsed by tsunami force. This was reconstructed in this way. GRS embankment now facing is under construction. This is expected to work as a tsunami barrier. So a number of conventional type embankments, retaining walls, and bridge collapse by recent severe earthquake, heavy rainfall, floods, storms, and tsunami in Japan. Many of them were restored to GR structures with full height facing because of their characteristic feature, including fast restoration. Second, high stability against natural disasters, even when constructed at a topographically difficult site, that is slopes, for example, slopes, and low cost for construction and maintenance. Okay, the conclusive remark. So this is the history of GR structure I explained today, starting from 1998. The research was started in 1982. This is a test embankment we constructed in 1982. These are my two daughters at the time. This is 14 years later. So this is showing a GR's retaining wall with the full height ridge facing of a commuter railway cable line very close to my house. This is 24 years later. This is Nagano GR retaining wall, 15 years after construction. So they got married. And this is 29 years later. This is a GR retaining wall for commuter train cable line. This is 70 years after construction. Now the number of families increased. You can see 3 grandchildren. This is 36 years later, full-scale model for GR Indian Bridge at the Railway Research Institute, the 8 years after construction. So now grandchildren is the number is 4. So conclusion 1, A number of GIS written wall having stage constructed fluid spacing and related GIS structure have been constructed as an important permanent soil structure for a total length at about 200 km, including those for high-speed railway Shinkansen. This accomplishment is due to their high cost effectiveness by high performance during long-term service and against severe earthquakes, heavy rainfalls, and low cost for construction and maintenance. GIS bridge abutment supports a simple girder with a fixed bearing at the top of the fluid facing of GIS wall. This is much more cost-effective and much more stable than the conventional type abutment. About 140 GIS bridge abutments have been constructed. Since the open to service, all exhibited practically zero bump. The GIS bridge abutment is now one of the standard bridge abutments for railway in Japan. GIS interior bridge structurally integrate both ends of a continuous girder to the top of the fluid facing of a pair of GIS written wall. Not using a bearing, this is much more cost-effective and much more stable than conventional simple girder bridge. GIS integral bridge is now one of the standard bridge systems for railway in Japan. A great number of conventional type embankments, retain wall, and bridge collapsed by recent severe seismic loads, heavy rainfalls, floods, tsunami. Many of them were restored to GIS structures having stage construction fluid facing. The following are three key breakthroughs for the development of the GIS structure explained in this presentation. First is the use of fluid facing for change from a low earth pressure to high earth pressure at facing. B, from facing as a secondary non-structural component to the facing as a primary structural component. Second is construction for change in construction from backfill after facing to the backfill before the facing. So third is structure integration for reinforcement, backfill, fluid facing, and girder for a change from a statically determinate but less stable structure to statically indeterminate but more stable structure, particularly with GIS bridge abutment and GIS integral bridges. So the PDF file of the related technical papers of GIS structure by Tatsuga et al. Can be downloaded at this homepage. And finally, this is showing a 3R association, which are managing and controlling the construction of the GIS structures, reinforced structure with digit facing. So homepage is this. You can visit this homepage. Thank you very much for your kind attention.
Well, that was an incredibly good presentation. Thank you so very much for preparing all this information. Press for she. I see this. I have questions here so far, and I have one of my own as well. So the first one is about the embedment depth. This is from Avik Kumar Mandal, who I think is listening from India. He said, "Professor, a very, very interesting and thoughtful talk. What should be the minimum required depth of foundation embedment for the full height casting a better sturdy? Please discuss." I hope you could follow that. It's about the recommended embedment depth of the facing. I think you're muted. From you might be muted.
50 centimeter. Generally, I think 50 centimeter.
50 centimeters.
Yes.
Right. There's a simple answer. Yeah. Yeah. Are there any situations where you might recommend a deeper embedment or even less, maybe depending on the foundation condition?
Well, we don't need a deeper one because bearing capacity of the ground below the facing is not a design component. So 50 centimeter enough. Excavation, if we use a deep foundation, we need excavation. So it increases the cost.
Yes, of course. Okay.
However,
thank you.
Okay, one point.
Yeah.
For breach abutment, the stiff bearing stiff subsoil is necessary. Soft, in that case, usually we use a good soil foundation. Otherwise, some shallow ground improvement.
Okay.
To ensure the small residual settlement.
Yes, that makes very good sense. Of course, yes, for bridge abutments we can't be supporting that load on the soft soil, of course. Okay, and we have a question, another one from Zoe Lin. It is quite a short question. It says, as we know, lots of PVA geogrid are used in the Japanese high-speed railway. Is it really necessary, and why?
Minimum requirement is that zero textile must strong against high pH. So, for example, polyester is not good. Other HDB is acceptable, but in our case, all any type of the textile is examined, checked with respect to the durability against high pH. This is performed by Railway Technical Research Institute. They are giving approval.
Yeah, I assume now that's because it's coming into contact with concrete. Is that right?
Yes, yeah. Exactly.
Yeah. Okay. Actually, I also have a question for you, because in most of your sections, you show your conventional arrangement of geogrid, where the geogrid is shorter at the bottom of the wall than at the top. Yeah.
Yes.
But you did have one or two sections where the geogrid was longer at the bottom of the wall and shorter at the top. So is there any technical reasoning or anything about that particular arrangement of the reinforcement?
For bridge abutment, the stability is really important. Overturning and sliding we have to avoid. So to have a stable back approach field, the longer one at the bottom is better. This is by experiment and analysis. But ordinary retain wall, very often we have a construction on slope. If we use a longer one at the bottom, the problem of excavation becomes very serious. So short at the bottom, if this worked, this is very convenient arrangement.
Yes, clearly, yeah. So there's another question which might also interesting from Avik Kumar Mandal again. He said, is there available a guideline for design and construction of the full height panel system for both walls and bridge abutments? And does the available BS 8006 or FHWA guideline for the wraparound facing, can that be followed? Please, could you provide some help for Avik?
Actually, the design standard, design manual, construction standard, construction manual, and material manual It's a really big amount in Japanese. And I translated, and my colleague translated part of the design standard for railways and the design manual in English. So I think this was provided to Indian Railway Ministry of Indian Railway, because they are accepted to construct their structure for some part. So the other one, I think we can open some. We are opening some document in English. So I'll check how that can be available to other people.
Is that something that the Indonesian chapter could distribute to the people who are listening to the webinar?
But
that'd be very helpful. Please check first.
I am not the owner of the document.
No,
so,
I understand that. But if it is something that we can get, it would be very helpful.
Yes. I talk to the person in charge. I think it's quite possible. I think.
Right. Okay. We have a question from Kianush Hatami. I'm guessing maybe from Japan. How long do they typically have to wait for the deformation of the GRS mass to take place before the full height facing can be cast into position? How long?
It depends on soil conditions. Yeah. This is observational method. The settlement is observed. If the settlement has taken place sufficiently in short time, 1 week, 2 weeks possible, but it will take a long time. In that case, we may perform a preloading to accelerate the settlement. So all depends on the rate of settlement actually taking place. So it's a soil mechanics program.
So
no standard.
Yeah. So it's no standard. But does this mean then normally you recommend there is some kind of monitoring to measure the deformation of the facing? So yes. Right. That's an important feature, I guess.
Yes.
So settlement
to the
top or outward deformation? Outward or just settlement? Right.
The bottom of the facing. Bottom of the facing. Actually, the engineer measuring the settlement at several places, but the key point is the bottom of the facing.
Right. That's
wall face. Sorry, but bottom of the wall face.
Bottom of the wall face. Okay. Now that's it. I have another question for you myself, because I'm always very interested to learn about reinforced soil structures that have actually been subjected to very strong earthquakes. And I'm very aware of some in New Zealand, which I was involved with. But I'm guessing with all of those walls that have been built and designed on the high-speed railway in Japan over so many years, I mean, many of them must have been strongly shaken by now by strong earthquakes.
Yes.
So, yeah.
So far,
are there any kind of records of the likely ground accelerations that may have taken place under these walls?
The railway engineers in charge check whether there is damage or not. So no report about damage or settlement, but no seismography graph at the wall. But nearby one we can find. It's from network of seismographies.
Because I know in New Zealand we had one wall which was actually next to, it was next to a railway line, but this one almost certainly up to 0.6 G.
Oh, 0.6 G.
Yeah, so it was very strong. That was the Kaikoura earthquake.
Sorry. Kobe earthquake. A long time ago, there we find a seismograph record that we analyzed. Afterwards, no serious analysis should be done.
I mean, I think this experience seems to me to be very important for engineers here in Indonesia, because obviously, as you well know, Indonesia also is a highly seismic place. We have a lot of subduction zone, so I think the experience you described today is very valuable for engineers designing structures here in Indonesia. And again, I enjoyed very, very much your presentation, Fumio, and thank you again for doing that. We have no more questions. I know we might have one more question. Let me just see. I think one more just came in here. Oh, from Mr. Avik again. Oh, we have, I think, probably the last question from Mr. Avik. He says, how does the precast segmental facing for retaining walls, precast segmental wall, how can that be compared to the full height? In other words, the full height wall system that you described just now, in consideration of long-term performance in both static and seismic conditions, which one would be more preferable? I think we know your answer to that.
For severe seismic motion, the full height is better. But for ordinary condition, we don't know. It's difficult to find which is better. However, for railway structures, we have many structures on the top, and electric pole, supply pole, or noise barrier, and so on, so on, so on. And then the full height lead facing is really convenient. Very I mean, the full height lead facing can support such an external load. This is practically very, very advantageous.
Yeah. No, I can see that. It certainly is, yeah. Okay, well, so one more question here. It's also from Zoe Lin. For GRS bridge abutment, is it better to use sand or gravel backfill to reduce the bump, especially for high-speed railway?
Well, okay. So theoretical, the sand is acceptable, but in Japan so far, this is a high-speed railway, and the railway engineers are very conservative. So they are using a well-graded gravity soil so far. But for road, maybe we can use sandy soil, if that is well compacted.
Yeah, I think that's very good advice as well. Yeah, I think no. Okay, well, I think that's we've come to the end with our questions are finished. There were some very good questions there. So I think Fumio, I can let you take a rest now because it's getting quite late in Japan. I would like to thank you again for providing this wonderful presentation. We will distribute a PDF of your work to the people who are listening in, and I hope you'll be coming to visit Indonesia again quite soon.
Okay. Thank you very much for your attention.
No, well, thank you also. Well, we will close down this presentation part, but if you would like to watch the quiz, then if you follow the instructions, you can see how people do on your questions.
Okay.
Okay. Bye then, Fumio. Thank you very much again.
Bye-bye.
And I will hand back to Rifa and